we shall going to start module 3 of chapter 3. In this module, we are interested to discuss dissipative function and related matters. In a conservative dynamical system, the sum of kinetic energy and potential energy remains constant. But if in a system the mechanical energy does not remain constant, then the constant is called dissipative type. In such cases, the constant forces do some works. As a result, the mechanical energy remain dissipative. For such type of system, we have to add the dissipative forces in the Lagrangian formulation. In this module, we shall incorporate the dissipative forces in the Lagrange's equation of motion. In this module, we shall discuss Rayleigh's dissipation function. First of all, we shall study the dissipative function and its physical interpretation. Later on, Lagrange's equations of motion will be derived incorporating the dissipative function. Next, we shall discuss theorem on total energy. First of all, let us discuss Rayleigh's dissipation function. Consider a dynamical system in which the principle of conservation of energy does not hold. We know that if in a dynamical system the conservation of energy holds, that is, sum of kinetic energy and potential energy remains constant, then such dynamical system is known as conservative dynamical system. But if the constraint forces do some work during the constrained motion, then the energy becomes dissipative. Example of such a system is frictional system. We shall now consider such system. Let us consider a dynamical system which is specified by n generalized coordinates small q1, small q2 up to small qn. Let kinetic energy T be the function of generalized coordinate qe, generalized velocity qe dot and time t. Here qe dot means ddt of qe, that is ordinary derivative of qe with respect to time small t. We have already obtained Lagrange's equation of motion corresponding to the coordinate qe, which is given by ddt of del capital T del qe dot minus del capital T del small qe equal to capital qe star. This equation is valid for E equal to 1, 2 up to n. Here del capital T del qe is the first order partial derivative of kinetic energy capital T with respect to generalized coordinate small qe. Qe dot is the generalized velocity. Capital qe star is the generalized force associated with the generalized coordinate small qe. The generalized force capital qe star can be written as summation over I capital Fi vector dot del del qe operated on Ri vector, where capital Fi vector is the applied force which is acting on the ith particle having mass mi and its position vector is Ri vector. Here dot means we are considering the dot product or scalar product of two vector quantities which are force Fi vector and del del Qe of Ri vector. Let the generalized force capital Qe star can be written as sum of capital Qe 0 plus capital Qe. 0 is used as superscript. The potential forces are given by capital Qe 0 which is minus del del Qe operated on capital V, V being the potential function and capital Qe corresponds to the non-potential forces. Let the non-conservative forces are of the nature of frictional forces. We know that frictional forces always resist the motion of the particle and it is proportional to the velocity. So, if capital Fxi, capital Fyi, capital Fzi are the components of the force F vector along the x axis, y axis, z axis, then capital Fxi is equal to minus c suffix xi into xi dot. Xi dot is the velocity component along the direction of x axis, which is the ordinary derivative of xi with respect to time t. As we have already mentioned that frictional forces always resist the motion of the particle, so we have the negative sign, and frictional force is always proportional to the velocity, so Cxi is the proportionality constant. Similarly, we get capital Fyi and capital Fzi, where Cyi and Czi are the proportionality constant and yi dot and zi dot are the components of velocity along y and z direction respectively. Here the proportionality constant Cxi, C suffix yi, C suffix zi are independent of velocity components xi dot, yi dot and zi dot. The virtual work done due to virtual displacements delta Ri vector is given by delta W, which is the sum of capital Fi vector dot delta Ri vector. Here dot means we are considering the scalar product of two vector quantities, which is force vector Fi vector and the displacement vector delta Ri vector. As we are considering the virtual displacement, so we get the virtual work. It is well known that work done is the force into displacement. So, we have delta W equal to summation over I Fi vector dot delta Ri vector. If we substitute Fi vector as Fi vector equal to capital F suffix xi into I vector, capital F suffix yi into j vector plus capital F suffix zi into k vector, and in a similar fashion if we write delta Ri vector as delta xi into I vector plus delta yi into j vector plus delta zi into k vector, then taking the dot product we get the right hand side. After substituting the expression for capital F suffix xi, capital F suffix yi and capital F suffix zi, we get the next line. Now, Ri vector depends on generalized coordinates q1, q2 up to qn and time t. So, let us calculate delta Ri vector, which is the virtual displacement. delta Ri vector is equal to summation over E del del QE operated on Ri vector into delta QE. This can be written as summation over E del Ri vector dot del QE dot into delta QE. We have already obtained the result del del QE of Ri vector equal to del del QE dot operated on Ri vector dot. In previous module, we have used that result here. In component form, we can write the above equation in this way, that is delta xi equal to summation over E del del QE dot operated on xi dot into delta QE. Similarly, we can write delta yi and delta zi. Substituting in the expression for delta w, we get this equation. Rearranging this, we get the next line. The above equation can be written like the equation given in this line. Here we have written the above equation in the differential form. Arranging the summation, we get the next line. This is the expression for f. Substituting f here, we get delta w equal to minus summation over E del del QE dot operated on capital F into delta QE. Here capital F, which has this expression, is the Rayleigh's dissipation function. If we differentiate the previous equation with respect to QE partially, we get del del QE operated on W equal to minus del del QE dot operated on capital F. This result holds for E equal to 1, 2 up to small n. N is the degree of freedom. The dissipative generalized forces are capital QE, which can be written as capital QE equal to minus del del QE dot operated on capital F. Here we have just used this result. QE dot is the generalized velocity. Now, Lagrange's equation of motion can be written as ddt of del capital T del QE dot minus del capital T del QE equal to minus del capital V del QE minus del capital F del QE dot. This is valid for E equal to 1, 2 up to n, since we are considering a dynamical system having n degrees of freedom. T is the kinetic energy, V is the potential energy, capital F is the dissipative function, small q suffix c is the generalized coordinate, QE dot is the generalized velocity, small t is the time. Shifting the terms on the right hand side into the left hand side, we get this equation. We have combined the terms of similar nature and get this equation. This is valid for E equal to 1, 2 up to n. If we put L equal to capital T minus capital V, then the above equation can be written as ddt of del del QE dot operated on capital L minus del del QE operated on capital L plus del capital F del QE dot equal to 0, where L is the Lagrangian of the system. Let us interpret physically the dissipative function. Let a particle is moving under the external resisting force which is proportional to the velocity of the particle. Then rate of work done by the system against friction is the energy lost to the system by the action of the resisting forces, which is minus of minus Cx into x dot x dot minus Cy into y dot minus Cz into z dot z dot. Please note that we are considering rate of work done. Work done is equal to force into displacement, which is, this is the force component Cx into x dot, x is the displacement, force into displacement gives the work done. We are considering rate of work done, so we get x dot. Rate means we are taking the time derivative with respect to t. This result can be combined as Cx into x dot square plus Cy into y dot square plus Cz into z dot square. Here x dot means dx dt. Writing this equation in this form, we simply get 2 into capital F, where F is the dissipative function. Thus, we have 2 into capital F as the rate of energy dissipation due to the action of the resisting forces. In our previous module, we have obtained that Lagrangian is the difference between the kinetic energy and potential energy. This will be used to obtain the theorem for total energy, which will be discussed in this case. Let us discuss the theorem on total energy. For a scleronomous conservative dynamical system of n degrees of freedom, the quantity summation over k qk dot into del L del qk dot minus L is a constant of motion, where q1, q2 up to qn are the generalized coordinates, L is the Lagrangian. By a scleronomous system, we mean that the system is independent of time t. As the system is conservative, so the mechanical energy remains constant. There are n degrees of freedom, so the generalized coordinates q1, q2 up to qn are sufficient to specify the position of the dynamical system completely. Let us prove this theorem. As we are considering scleronomous system, so L will depend on generalized coordinate qk and qk dot. Please note that t is absent here. Taking the time derivative, we get dl dt, which can be written as summation over k del L del qk into qk dot plus summation over k del L del qk dot into qk double dot. As L depends on qk, we first differentiate L partially with respect to Qk and then differentiated Qk ordinarily with respect to time t and get the first term of the right hand side. Again, as L depends on Qk dot, so we have differentiated L partially with respect to Qk dot and then differentiated Qk dot ordinarily with respect to time t and get Qk double dot. We have used the chain rule of differentiation here. Thus, ddt of summation over k Qk dot into del L del Qk dot minus L can be written as, first of all let us differentiate Qk dot with respect to time t, keeping del L del Qk dot fixed, we get the first term of the right hand side, which is summation over k Qk double dot del L del Qk dot. Next, keeping Qk dot fixed, we differentiate this term, that is del L del Qk dot with respect to time t ordinarily and get the second term of the right hand side. Next, differentiating L with respect to time t ordinarily, we get dl dt. If we substitute dl dt from here, we get the last line. First and last term cancels each other, so we have only these two terms, this term and this term. Thus, we can write this. This is nothing but the Lagrangian equation of motion corresponding to the generalized coordinate Qk. So, the right hand side vanishes. We get it using Lagrangian equations of motion. Thus, in such a system, the total energy, which can be written as E equal to sum of kinetic energy and potential energy, is constant. Since this is 0, one can conclude that summation over k Qk dot del L del Qk dot minus L equal to constant. Let us prove it. L is the Lagrangian of the system, which can be written as the difference between kinetic energy and potential energy, where kinetic energy T depends on generalized coordinate and generalized velocity and potential energy depends only generalized coordinate. Now, E equal to summation over k Qk dot del L del Qk dot, here L has been replaced by T minus V minus L, here also L has been replaced by T minus V and we get this result. Since del del Qk dot operated on capital V equal to 0, so we can write this equation. In a scleronomous system, kinetic energy is a homogeneous quadratic function of generalized velocities. We have proved this result in the previous chapter. Using this, we can write the above equation as capital E equal to summation over k Qk dot del del Qk dot operated on capital T minus T plus V. Here we have used del V del Qk dot equal to 0. Now, this is twice T. Using this result, we get twice T minus T plus V, which on simplification becomes T plus V. So, in such a system, the total energy is conserved. In this module, the reformulation of Newtonian mechanics which is known as Lagrangian formalism, has been discussed. Moreover, it is associated with the configuration space and time and has been extended to incorporate the dissipative forces.